Today we are going to continue on chapter 5 on the topic of transient conduction. Last week we learned about the lump capacitance method and spatial effects, in particular in planar wall and radial systems. This week we are going to focus on semi-infinite solids and numerical methods. Let's start with the semi-infinite solids. So before we do any analysis, I would like to just show you different types of geometries that you can encounter with this semi-infinite solid type of problems. So there are three cases. In case 1, we have a semi-infinite object that is extending infinitely in x direction, and the boundary condition is Ts. The surface temperature is fixed, it is given, it is Ts. This is case 1. In case 2, we still have a semi-infinite object. It extends infinitely in x direction, in positive x direction. And on the boundary, we have constant heat flux, and which is given. Okay, this is case 2. In case 3, we have again a semi-infinite object extending infinitely in positive x direction, and we have convection at the surface, at the boundary. So the convective flux is equal to conductive flux at the interface. And before we do any analysis, I just want to show you the solutions. I want you to pay attention the behavior of the graphs. So as you can see here, all of these graphs, like in terms of shape of the curves, they have this monotonically decreasing functions as shown in here, in case 1, case 2, and case 3. Obviously the intercept values are slightly different, but overall the shape of the curves look very similar. So that should give us a hint about the potential solution for this type of problems. Okay, so that is the first observation before we do any analysis. So now let's switch back to whiteboard. We are going to derive and analyze this problem. Okay, in the previous slide I just showed you 3 different cases of semi-infinite objects, and as we just talked about, although the boundary conditions are different, the behavior of the temperature profile looks very similar. So this is actually not an exception. In many of the transport problems, transient transport problems, when you are dealing with semi-infinite objects, so you obtain a solution that depends on position and time at the same time. You obtain a solution which depends on position and time at the same time, not as independent variables, but a combination of position and time will always appear when you are dealing with semi-infinite objects. So what does it mean? So to be able to better understand this, let's talk about the dimensional analysis. Dimensional analysis. So in heat transfer, we are analyzing the heat diffusion equation. In this case, we have d squared T by dx squared divided by 1 over alpha, which is equal to dt by d time. This is the equation that we need to solve to obtain a time-dependent temperature. So if you just do a dimensional analysis in this system, you'll see that there is a dimensionless number, which is alpha times T over L squared. So alpha is thermal diffusivity. Its units are meters squared per second. Time, units second. Length, the units is meter squared. So as you can see, this is dimensionless. Likewise, if you do in fluids, we had nu, this is kinematic viscosity, times T over L squared. This is another dimensionless number. This is dimensionless. 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 In mass transfer, some of you are already taking this class. So diffusivity times T over L square is another dimensionless number. Okay? So now let's use this information. So we just stated that when you are dealing with a semi-infinite object, the solution temperature profile, time-dependent temperature profile, depends on position and time in a particular way. They are not random function of x and random function of t. You have a combined function of x and t that will always propagate through the system. So how do we guess that kind of functional dependence? So we can rely on dimensional analysis here. So we just mentioned in heat problems we have alpha times t over L square is dimensionless. That means alpha t square root over L is also dimensionless. Both of these are dimensionless. This is dimensionless. So now, if this is correct, so I would like to propose that. So I have a variable, a similarity variable, which is dimensionless, can be written as x divided by alpha t square root. Okay, so again, right now I'm making a proposition. So for the sake of mathematical convenience, okay, in terms of dimensional analysis, this form is correct, but it is better to use the following form just to make the calculus easier, because we are going to do several calculus steps here. So I want to use this 4. 4 is a constant. It doesn't have any dimensionality. So the boundary conditions will take care of it. So I would like to start with this. This is mathematically more convenient, okay? Mathematically more convenient. So this is my starting point. So what I'm proposing is I have a dimensionless variable eta, so which depends on x and t in this particular form. It doesn't have x plus, it doesn't have multiple functions. So the solution will only depend on eta, and that will have x over square root of t dependence everywhere. That is the idea, and that is the hypothesis. If I can obtain a solution like this, then I have the solution. So now this is the similarity variable. This is what I want to start with. This is what we call as similarity variable. Similarity variable. Okay. So now what I'm going to do, I'm going to focus on one of the cases, case 1. Let's talk about case 1. In case 1, what did we have? We have a semi-infinite object. So this is x direction. This is positive x direction. So here x equal to 0. And we measure the temperature at the wall, and which is given to be T sub S. And this is positive x direction. So the boundary conditions, initially, object is at Ti everywhere. So that means at all x positions, when time is equal to 0, temperature is Ti. And for all times after t is greater or equal to 0, so the surface temperature is given to be Ts. So this is the boundary conditions, and boundary condition and time dependent condition. And the governing equation is heat diffusion equation, d squared T by dx squared plus 1 over alpha dt by d time. So now let's use the similarity variable here. So I would like to write these terms in terms of the similarity variable now. So I don't want to have temperature. I would like to work with a similarity variable now. So to do that, I need to use the chain rule. So I need to express the other terms in terms of the similarity variable now. So my goal is to express the other variables in terms of similarity variable now. So we have dt by dx. So if you apply the chain rule here, so we have dt by the eta and the eta by dx. Okay, so you can see these two terms cancel and you will get dt by dx. So now, so dt by the eta is the new variable that I'm trying to find, and the eta by dx is, it can be calculated. Since I have an expression, I have a proposed expression for eta. So the eta by dx from this equation is 1 over 4 square root of alpha t. So I can substitute that expression in here. So I have 1 over 4 alpha square root of t. Okay, so that is d by dx, but I need the second derivative, so that means I need dt by dx by dx. This is the second derivative, so that means I need dt by dx by d eta by dx. So now I know what the dt by dx in terms of the eta here, and the eta by dx we already calculate that one. So this term d square t by dx square is equal to d, and this is dt by the eta 1 over 4 alpha t square root by the eta, and the eta by the x is 1 over 4 alpha t square root. So now t is constant with respect to eta, and that means I can pull this term outside the integral, outside the derivative, and combine these two terms. So then I have 1 over 4 alpha t d squared t by the eta squared. So this is the transformation of d squared t by the x squared. So this is the first piece of the heat diffusion equation. So now I need to express dt by d time in terms of the similarity variable. So I'll be doing the same trick. I'll be using the chain rule, dt by the eta by d time. So in this case, I'm going to leave the time derivative as it is, and I'm going to try to calculate this from the definition of the similarity variable, which is, so we have eta is equal to x for alpha t square root. So the eta by dt is equal to, so with respect to t, these terms are constant. So we have x over 4 alpha, and this is t to the minus 1/2, and if I take the derivative, I'll have minus 1 over 2 multiplied by t to the minus 3/2. So if I combine everything, so I have minus x over 2t for alpha t square root. Okay, so t times square root of t in the denominator will give me t to the minus 3.5. So now what I'm going to do, I'm going to combine these two. So the heat diffusion equation was d squared t by dx squared plus is equal to 1 over alpha dt by d time, and I express each of these terms in terms of similarity variable. So I have d squared t by the eta squared multiplied by 1 over 4 alpha t multiply is equal to 1 over alpha and this is dt by d time is basically dt by d eta multiplied by minus x over 2t for alpha t square root. Okay, so everything is multiplication here. So we need to tighten this equation up, and we need to organize this a little better now. So now let's focus on here. So we want to reorganize this equation. So we have d squared. Since now I want to, before I do the reorganization, since I only have one variable eta, I'm going to switch to ODE. Only t is only function of eta. So I'm switching ordinary differential equation now from partial differential equation, since I only have one variable. So I'm going to organize this a little bit. So I have dt by d eta so now I have 4 alpha t divided by alpha divided by 4 alpha t square root divided by 2t multiplied by x, and there is a negative sign in here. Okay, so now let's organize this a little better. So we have, let's focus on this term now here. So we have these alpha terms will cancel, t terms will cancel, so this 2 will cancel. So we have 2 x over 4 alpha t in square root. And if you pay attention to this term, this is the definition of the similarity variable. This is eta. So that means my ordinary differential equation becomes d squared t by d eta squared is equal to minus 2t, so not 2t, 2 eta to eta dt by dn, and this is an ordinary differential equation. So now, so far so good. So we replaced x and t with eta. We only have one function, one functional derivative. So we need to also take care of the boundary conditions, boundary condition and initial condition. So the initial condition, so we had at x equal to 0, t was equal to ts. So how do I express x equal to 0 in terms of new variable eta? So x equal to 0 correspond to, if you take a look at the definition of the similarity variable, so x equal to 0 means eta is equal to 0, because it is x divided by 4 square root of alpha t. So x equal to 0 means eta is equal to 0. And for t is equal to 0 or x equal to infinity, t was equal to ti. And for this case, for these two cases, t goes to 0 or x goes to infinity. This means eta goes to infinity. And in this case, t is equal to ts. Here, t is equal to ti, initial temperature. Okay, so our boundary conditions now, so we have a second order ordinary differential equation, and we have two boundary conditions. That means we should be able to solve this equation. So now let's do the calculus here. So let's rewrite this equation as, so dt by d eta divided by d eta is equal to minus 2n dt by d eta. Okay. So now what I would like to do, so I can call this dt by d eta as u. So that means we have du by d eta is equal to minus 2 eta u. So that means du by u is equal to minus 2 eta d eta. So if I integrate both sides, so then I will obtain ln u is equal to minus I'm going to divide it by 2, so 2 is going to cancel, minus eta square plus an integration constant. Let's call this as C1. Okay, so this is the integration constant. Okay, so now if I continue here, so I can take the exponent of both sides. So we have e to the ln u is equal to e to the minus eta square plus c1. Okay, so e to the ln u is going to give us u, and is going to give us, we can separate this as e to the eta square multiplied by e to the c1, and since c1 is constant, e to the c1, I can call this as c1 star, a new constant. So that means u is equal to c1 star e to the minus eta square, and u is the variable that I just introduced here. So that means dt by d eta is equal to c1 star e to the minus eta square. Okay, so this is the equation. So I can rearrange this slightly. So I can call this as dt is equal to c1 star e to the minus eta square dn. So if I would like to calculate t at any time or at any eta value, so it is c1 star integral from 0 to eta exponential minus s square ds. Okay, so here plus a constant. So s here is the dummy variable. So mathematically speaking, I shouldn't be using the same symbol here, eta and eta, so I need to introduce a dummy variable to be mathematically correct. So this is just a dummy variable, it doesn't have any significance. So that is the dummy variable here. Okay, so now we have two constants, c1 star and c2, and we need to find them. So how are we going to find these? So the boundary conditions, we need to rely on boundary conditions. When eta is equal to 0, t is equal to ts. So now what does eta equal to 0 mean? Integral from 0 to 0, that means it is 0, so we are not integrating. So that means t c1 star integral from 0 to 0 is going to give us a big 0 here. And then we have c2. So that means, and t in this case is equal to ts. So that means c2 is equal to ts. So now we found one of the boundary conditions. The second boundary condition is, as eta goes to infinity, t is equal to ti, and this is equal to c1 star integral from 0 to infinity exponential minus s square ds plus ts. So that means ti minus ts is equal to c1 star integral from 0 to infinity exponential minus s square ds. So now we are almost done, but there is this tricky situation here. how do we carry out this integral? Okay, so this integral can be carried out in various ways. You can use Laplace transforms, you can use Fourier integrals, you can use Cauchy integrals. So this is actually a little advanced topic. So I'm not going to keep you responsible for carrying out this integral, but I'm going to tell you what is the solution for this integral. So this is just a general information for all of you. So if you have this integral, let's put as a side mark. Whenever you see this integral from 0 to infinity exponential minus x squared dx, this is always equal to square root of pi over 2. This is a known integral, so you don't need to memorize this, but you need to remember when you are dealing with e to the minus x squared, this can be y, z, any letter you like, as long as we have these two here in the exponent and in the differential, the solution of this integral is square root of pi over 2. So that means if I substitute this piece of information here, if this term is square root of pi over 2, so that means C1 star is equal to Ti minus Ts over square root of pi, and everything is multiplied by 2. So now I have C1 star, I have C2. So the solution for so far, T is equal to C1 star is 2 times Ti minus Ts divided by square root of pi from 0 to eta exponential minus s squared ds plus ts. So I can organize this a little better. So I can pull the ts on the other side, divide this by Ti minus Ts. So we have T minus Ts divided by Ti minus Ts is equal to square root of 2 pi from 0 to eta exponential minus s squared ds. Okay, so this is the solution of the temperature profile. So however this, before I actually go some more, I want you to realize one more thing. I explained to you what is the integral when it goes from 0 to infinity, it is equal to square root of pi over 2. But this integral also, if you have an integral of this form, this is a side information, the square root of 2, so 2 over square root of pi from 0 to x exponential minus u squared du. This function has a special name. It's called error function. So this is error function. Okay. Again, this is another integral that you may not be aware of, but I'm giving you as a side information, and you don't need to memorize this. This will be always given to you, available to you. So let's use this information here. If I use this information, I can further simplify my equation, and it will be T minus Ts divided by Ti minus Ts is equal to error function eta. So I have the full solution now. I have the full solution. And again, I have the eta. I have the eta that was defined as x over 4 alpha t in square root. Okay? So now I have temperature dependence with respect to x and t as given in this equation. And okay, so this is the main solution. So this is for case 1. I obtained the solution, and the solution turns out to be an error function. And if I need to calculate the heat flux at the surface, so which is basically in case I need to calculate the heat flux for certain calculations, so I need to take the derivative of this term with respect to x. So that is k Ti minus Ts. So I'm substituting T here. So this expression is for the T term here. So this is T. So I'm taking dt by dx. So the constant will come from Ti minus Ts is coming from this denominator here. And then I'm going to write down the term as d error function eta by d eta and d eta by dx. So I apply the chain rule to differentiate it in terms of eta. So the derivative of the error function, if you take a look at here, if you take the derivative of this term, the integral and derivative will cancel, and you will end up with minus k Ti minus Ts 2 over square root of pi exponential minus eta square, and we already calculated d eta by dx, which is 1 over 4 alpha t in square root, and we are evaluating this at eta equal to 0. E to the 0 is 1, so I obtain the solution. I obtain the following solution: k. So k. So and there is a negative sign in here. Sorry, there is a negative sign, so I switch Ts and Ti, and then 2 and square root of 4 will cancel, so we'll have pi alpha t in square root. So this is the heat flux.